Hi everyone. In this particular session, we're going to discuss Jacobians. This comes under partial differentiation, and this has some of the very important applications in integral calculus and many other topics as well. So, in this particular session, we'll see how to define the Jacobian, and we'll also see some of its properties. And towards the end of this session, we'll see as to how to work out a few problems pertaining to Jacobians. So, to begin with, suppose we have x as a function of u and v and y as another function of u and v, then we define the Jacobian of x and y with respect to u and v as follows. Right? So how exactly do we define this? First of all, the Jacobian of x and y with respect to u and v is denoted by, just a minute, yeah, this is denoted by j, right? So this is defined as j of x comma y, just a minute, yeah, this is j of x comma y by u comma v. This is another denotation of the Jacobian of x and y with respect to u and v. Okay, this is also denoted as dou of x comma y by dou of u comma v, and this is defined as the determinant of x with respect to u, and then x with respect to v, and then y with respect to u and y with respect to v. In other words, this is basically determinant of dou x by dou u, dou x by dou v, okay, then dou y by dou u, and then dou y by dou v, right? So this is exactly how we define the Jacobian of x and y with respect to u and v, right? Similarly, suppose we have x to be a function of u, v and w, y to be a function of u, v and w, and z to be another function of u, v and w, then the Jacobian of x, y and z with respect to u, v and w is defined as, now suppose we have x, y and z, three variables which are functions of three other variables, then the Jacobian of x, y and z with respect to u, v and w is defined as j once again, and now this is j of x, y, z, so j of x, y, z with respect to u, v and w, right? Or as written earlier, this can also be understood as or written as dou of x comma y comma z by dou of u comma v comma w, okay, and second, yeah, it is defined as determinant of dou x by dou u, which is xu, and then dou x by dou v, which is xv, and dou x by dou w, which is xw. Similarly, the second row would be dou y by dou u, dou y by dou v, dou y by dou w, and then the third row would be dou z by dou u, dou z by dou v, dou z by dou w, right? So this is the expression for the Jacobian, and of course only if it exists it is defined in this manner, right? So this is exactly how we define the Jacobian of two variables with respect to two variables, or three variables with respect to three variables, and so on, right? For example, suppose x equals, say, r cos t, and y equals r sin t. So suppose x and y are defined in this manner, then we can have the Jacobian of x and y with respect to r and t as, here because x and y depend on r and t, the Jacobian will be the determinant of dou x by dou r, dou x by dou t, and then dou y by dou r, dou y by dou t. Okay, now because x is r cos t, what would be dou x by dou r? X is a function of r and t, so when you're differentiating x partially with respect to r, you will have to keep t as a constant, so accordingly cos t will be a constant, so dou x by dou r will be cos t into differentiation of r with respect to r is 1, so this will be just cos t. Similarly, dou x by dou t, now when you have to go for dou x by dou t, now you have to keep r as a constant, so r will remain as it is, and differentiation of cos t with respect to t is going to be minus sin t, right? So this will be dou x by dou t. Similarly, when you go for dou y by dou r, once again here sin t will remain the same, and differentiation of r with respect to r is 1, so dou y by dou r would be just sin t. And when you go for dou y by dou t, now you keep r as it is, and the differentiation of sin t with respect to t would be cos t, so this will be r cos t, right? So accordingly, now the Jacobian of x and y with respect to r and t would be, this would be, now xr, which is dou x by dou r, is going to be cos t, and then xt, which is dou x by dou t, would be minus r sin t, and then yr, which is dou y by dou r, is sin t, and then yt, which is dou y by dou t, is going to be r cos t. Okay, and now you'll have to expand this further and find value of this determinant. Of course, if you remember some of the properties of determinants, expanding this would become a little easier. For example, because in the second column you have r common everywhere, you can just take it out and you can write this as r into cos t minus sin t, and then sin t, and then cos t, and upon expansion this would be r into, what do you get it as, r into cos square t plus sin square t, which is 1, so this will just be r. So to conclude, in this particular problem or in this particular example, the Jacobian of x and y with respect to r and t is going to be r. Okay, so this is exactly how we define the Jacobian of two variables with respect to two variables, or as given here, three variables with respect to three variables, and so on. Right? Now, before we look into some more problems pertaining to Jacobians, we will look into some very important properties of Jacobians. Okay, so to begin with, the first property would be pertaining to finding Jacobians of composite functions. So what exactly this says is this: if x is a function of u and v and y is a function of u and v again, where u is a function of, say, r and t, and v is also a function of r and t, then yeah, so as you can see here, what's happening, x is a function of u and v and y is also a function of u and v. So accordingly we should be able to find out the Jacobian of x and y with respect to u and v by the definition of Jacobians, as long as it exists. Similarly, u is a function of r and t and v is also a function of r and t, which will tell us that we'll be able to find out the Jacobian of u and v with respect to r and t. And now the property that I'm going to talk about would be this. So as you can see here, x is a function of u and v, and y is also a function of u and v, right? And u is a function of r and t, and v is also a function of r and t. So effectively, if you look at this, x and y are finally functions of r and t, because of which we should be able to find out the Jacobian of x and y with respect to r and t. So that exactly is what this property says. The Jacobian of x and y with respect to r and t. Now the problem with finding the Jacobian of x and y with respect to r and t is that we do not know explicitly or straight away as to how x and y depend on r and t. So the Jacobian of x and y with respect to r and t is given by the Jacobian of x and y with respect to u and v, which can be easily computed based on these relations, and that multiplied with the Jacobian of u and v with respect to r and t, which again can be found out from these two relations, right? So the Jacobian of x and y with respect to r and t would be the Jacobian of x and y with respect to u and v times the Jacobian of u and v with respect to r and t. As you can see, this looks pretty much like the chain rule. Probably if you can write this using the other notation that I showed you a little earlier, dou of x comma y by dou of r comma t is going to be equal to dou of x comma y by dou of u comma v times dou of u comma v by dou of r comma t. This is exactly the first property that I want to discuss, which talks about the Jacobian of composition of functions, right? This is one property, a very important property to be discussed. Now the second property, which is equally important, goes this way. If x is a function of u and v and y is again a function of u and v, then as we all know, we can find out the value of j of x comma y with respect to u comma v, right? Now what if we'll be able to express u and v in terms of x and y, is what exactly this property says. Okay, so if x is x of u comma v and y is y of u comma v, and suppose the value of j is not equal to 0, the value of the Jacobian as defined earlier is not equal to 0, then we can find out something called the inverse Jacobian, and this inverse Jacobian is defined as the inverse Jacobian of u and v with respect to x and y. Okay, and this is defined as follows. I repeat, x is a function of u and v and y is a function of u and v. Accordingly, we should be able to write or find j, which is j of x comma y by u comma v. And suppose that value of j is not equal to 0, then the inverse Jacobian of u and v with respect to x and y is defined as follows. Now, how do you define this? First of all, the inverse Jacobian of u and v with respect to x and y is denoted by j prime or j dash. So this is j dash of, as I said, because it is the inverse Jacobian, this will be j dash of u comma v by x comma y. Okay, now how do you define this, or how do we get it, evaluate it? It is determinant of dou u by dou x, dou u by dou y, and then dou v by dou x, and then dou v by dou y. Okay, now this will exist only when the value of the Jacobian, the original Jacobian, yeah, the value of the original Jacobian, which is j, is not equal to 0. Okay, so if that does not become equal to 0, then we can define something called the inverse Jacobian of u and v with respect to x and y, and it is given by this expression. Okay, and very importantly, this is something we'll have to know. Okay, further, it so happens that j into j dash, when I say j into j dash, it is basically the product of j and j dash. It is always going to be equal to 1. Okay, so this is a very important result asset, so I would like to highlight this. Okay, so find out j and find out j dash. It so happens that the product of them is going to be 1. So basically the product of Jacobian and its inverse is always going to be 1, is what this property says. And very importantly, the inverse Jacobian exists only when the value of j is not equal to 0. Right? So these properties, actually the first one and the second one both can be proved very easily. So I'll leave that part to you. So if you're interested, you can try to go through the proofs, and you can actually try proving them by yourself. So things are going to be very easy as such. But due to paucity of time, I am not able to touch upon that. So I'll just make use of these properties when it comes to problems. Okay, and the last property is about another possibility of the value of j. So once again, we have x and y to be functions of u and v, and suppose j equal to 0, it means the value of j is equal to 0, then it so happens that x and y are going to be functionally dependent. What do you mean by functional dependence? That means x is, or x can be expressed as a function of y and or vice versa. What do you mean by vice versa? You can have x to be a function of y, or you can have y to be a function of x, and this happens when j, the value of j, is going to be 0. Okay, so this is the other property as to when the value of the Jacobian is equal to 0. We have seen the previous property as to what will happen if the value of j is not equal to 0, and in this property we are seeing as to what's going to happen when the value of j is equal to 0. So these are two very important properties that have to be remembered as such. Okay, now not just two, these are the three properties as such. So just 1 minute, just copy down these, and then we'll see as to how to work out a few problems pertaining to these. Yeah, so these are the three properties that we have discussed just now. So just to recall, the first property is about the composition of functions. So if you have x and y to be a function of u and u and v to be functions of r and t, then the Jacobian of x and y with respect to the final independent variables r and t is given by the Jacobian of x and y with respect to u and v, and then that multiplied with the Jacobian of u and v with respect to r and t, right? And the second property says if the value of the Jacobian is not equal to 0, then the inverse Jacobian of, see, if x and y are given in terms of u and v, then when you are trying to find out the inverse Jacobian, it's about expressing u and v in terms of x and y. Okay, so that's exactly what we are trying to do here. So the inverse Jacobian exists only when the value of the actual Jacobian is not equal to 0. In that case, we see that j dash of u comma v with respect to x comma y is given by, which is actually defined as dou u by dou x, determinant of dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y, right? This is how we find out the inverse Jacobian, and it so happens that the product of the Jacobian and its inverse is always going to be 1 as long as j is not equal to 0, right? This is the second property, and the third property talks about the case when the value of the Jacobian is equal to 0. So if j is going to be equal to 0, then x and y turn out to be functionally dependent. And what do you mean by functional dependence? It means that you will be able to express x in terms of y or y in terms of x, provided the value of j is equal to 0. In fact, it is not actually an if then statement, it is an if and only if statement. What do you mean by an if and only if statement? It means that if x and y are functionally dependent, the value of j is going to be equal to 0. And if the value of j is equal to 0, then x and y are functionally dependent. And of course, if j is not equal to 0, it means that x and y are functionally independent. And that tells you that x and y cannot be expressed in terms of two variables. That means x cannot be expressed in terms of y and y cannot be expressed in terms of x as long as j is not equal to 0. Right? So these are three very important properties pertaining to Jacobians. Now based on all these things, we will see as to how to work out a few problems. Okay, so to begin with, we will take up a very simple problem. If say u equals x square y minus x y square and v equals xy, then find j of u comma v with respect to x comma y. A very simple question which could be easily asked for 2 marks in the examination. Okay, yeah, how do we do this? So to begin with, we'll see how to define j of u comma v by second j of u comma v divided by x comma y. How do you define this? By the basic definition of Jacobian, this is determinant of dou u by dou x, dou u by dou y, okay, and then dou v by x and dou v by dou y. Now this is equal to determinant of dou u by x, dou x. The first term would be, yeah, so when you differentiate u with respect to x, in the first term you will have only x square into y, which on differentiation will give you 2x into y, right? And in the second term x square, which upon differentiation x will give y square, right? So this will be 2xy minus y square. And then when you go for dou u by dou y, now you will have to differentiate u with respect to y partially. So when you do that, the first term will be x square into 1, which is going to be just x square, minus, now the second term would be 2xy, because x is kept constant and differentiation of y square is 2y. So this will be x square minus 2xy. So that completes the first row. Similarly, now when we go for the second row, what do we get? Dou v by dou x. Dou v by dou x is obviously just y, correct? And dou v by dou y is going to be x as such, correct? Now this is the expression for the Jacobian, but of course we should not be stopping here. We'll have to expand this further. Of course, here if you observe a little carefully, there is a y common in the first column and there is an x common in the second column. So probably you can take both of them out, because expanding otherwise might be a little tedious. So I've taken y common in the first column, so I'll be left with 2x minus y, and this would be 1, correct? And in the second column, x minus 2y, because I've taken x common, and the second row second element would be 1, and this would be, because I've already taken that out, correct? Okay, and in the second column, expanding this would become a little easier, because I have a 1 and 1 become easier in the second row. So 2x minus y minus of x minus y. Over here would be x minus 2, 2x is going to be x, and then minus y plus 2y is going to give you plus y. So this will be xy into x plus y, or you can as well write this as x square y plus x y square. Now this is what is the Jacobian of u and v with respect to x and y. Looks simple, right? Okay, so now we take up another problem, a similar one, a little uh, more complicated, I can say. This one would be, I've chosen this to be this. So suppose we have x to be r sine theta into cos phi, and then y is say r sine theta into sine phi, and suppose z is r cos theta. Okay, so this is how we are given three variables x, y and z with respect to r, theta and phi. Okay, and now we are told to find out the value of dou of x comma y comma z by dou of r comma theta comma phi. Okay, so this is the question of consideration. So we are told to find the Jacobian of x, y, z with respect to r, theta, phi, where x, y and z are given in this fashion. So how do we start with? First of all, how do we define dou of x, y, z with respect to r, theta, phi? How is this defined as such? So we'll see what exactly this is, and then we'll go ahead evaluating this expression. Okay, so by the definition of Jacobian, Dou of xyz with respect to r theta phi would be about first differentiating x with respect to all the three variables. So that will give me dou x by dou r, dou x by dou theta, and then dou x by dou phi in the first row. Yeah, of course, there is one more thing that I want to tell you here. When I define the Jacobian, this 1 minute. Sorry. I think I went a little too behind. 1 minute. Yeah. So as you can see here, in this dou x by dou u and dou x by dou u and dou x by dou v are in the first row, and dou y by dou u and dou y by dou v and dou y by dou v are in the second row. So if you know properties, it's very easy to see that instead of writing dou x by dou u and dou x by dou v in the first row, I can as well write them in the first column, because the value of the determinant of a matrix and its transpose are going to be same. So you can close columns and it does not really matter at all. Okay, this is just one note that I should have told you earlier. Nevertheless, at least now I have told you, so you can try remembering it. Yeah. So going ahead. With this problem. Yeah. So the first row will be dou x by dou r, dou x by dou theta, dou x by dou phi. So as I told you just now, I can also write it as a column. So it should not affect the expression as such. Now the second row would be dou y by dou r, dou y by then dou y by dou phi. Third row will be this one row, dou y by dou r, dou z by dou theta, and then dou z by dou. Okay, so this is how we define the Jacobian as such. Now how do we evaluate this? So now each term has to be computed. Dou x by dou r. So as you can see here, x is defined as r sin theta cos phi. So when you are differentiating this with respect to r, both sin theta and cos phi are going to remain as they are, and differentiation of r is going to be 1 because we are differentiating it with respect to r itself. So this will be sin theta cos phi. So this is dou x by dou r. Okay. Now dou x by dou theta, the next term, what would that be? Where do you get it as? So when you're going for dou x by dou theta, here r is going to be constant, phi is constant, so cos phi is a constant. So r cos phi will remain as it is. So this will be cos phi. Okay, so this is dou x by dou theta. Now dou x by dou phi would be, now r sin theta will remain as it is. R, sorry, r theta will remain as it is. That should be at all. That will give you minus sin phi. Okay, this will be minus sin. So you're going to get right the third term. Right now, for the second I'll give you theta and then sin phi for the same reason. Dou theta. Now this would be r cos theta, then sin phi, okay, and r sin theta. And differentiation of sin phi would give you phi. Okay. Now the last row, dou z by dou r. Dou z by dou r is going to be just cos theta. Okay. And dou z by dou theta. Dou z by dou theta will give you minus r sin theta. And dou z by dou phi. Now z doesn't have because of which 0 here. Okay. Now can you simplify this a little further before you expand the determinant as such? So as you can see here, there is an r common everywhere in the second column, as you can see, and there is an r sin theta common in the third column. Correct? So other than these two, I do not think there is anything else common to take out. So I'll take those two out. So the second column is going to give me an r common. The third column is going to give me an r sin theta common. So that will give me effectively r square sin theta. And what is left out? in the determinant, the first column would be sine theta cos phi. Now the first column is not changed at all, so I'll simply write it down as it is. So sine theta, sine phi, and cos theta. In the second row, sorry, in the second column, we have a cos theta, cos phi, then cos theta, sin phi, minus sin phi, minus sin phi, yeah. After this, I think it is better that we expand this straight away. Otherwise, I do not think you'll be able to simplify plus sin theta cos phi, correct? And then second term minus cos theta cos phi cos theta. Then the third term would be minus sin phi minus cos theta sin, correct? So this is exactly what I get. Looks very complicated, but if you simplify this carefully, you are going to get it as a very simple expression. So this is just sine square theta cos square phi, correct? And this is plus cos square theta cos square phi, correct? So in these two, if you take a cos phi common, you're going to get, oh sorry, cos square theta cos square phi, you're going to get this as, right? So the go for term by term multiplication and look for some common terms. It so happens that the value of this will simply become r square sine theta towards the end as such. You can try simplifying this a little further. You will be able to see that the value of this effectively will be r square sine theta. So to conclude, the I'm leaving the simplification process to you because I do not want to spend too much of time on basic simplification of this. As long as you're good at basic trigonometry, you will be able to simplify this further. So this will be r square sine theta, right? So this is how you will have to evaluate or find the value of the Jacobian of a function of two or more variables, and this is how you'll have to compute it as such. Okay, so with this I'm going to end with this session. So next session I'm going to continue with some more problems pertaining to Jacobians. So thank you for the patient listening. Go through the video carefully and try to work out these problems by yourself. I'll see you again. So thank you. Good night.